Dive deep into the mysteries of the universe as we explore the concept of cosmic inflation. Imagine, if you will, the universe in its infancy, a mere speck of intense energy and matter. This is where our story of cosmic inflation begins. Cosmic inflation, as the name suggests, is a theory that paints a picture of a rapidly expanding universe, a universe that grew exponentially in the first fleeting moments after its birth. Picture a balloon inflating, but multiply that rate of expansion by unimaginable magnitudes. That's cosmic inflation for you. This theory is not just a fanciful idea, but a key piece of the puzzle in understanding the early universe. It's like the opening chapter of an epic novel, setting the scene and introducing the characters for the grand narrative of the cosmos. But why is cosmic inflation so significant? Well, it provides answers to some of the most perplexing questions about our universe. Questions such as why the universe appears so flat and why it looks the same in all directions. It's like finding a compass in the vast expanse of cosmic wilderness, guiding our understanding of the universe's structure and evolution. The concept of cosmic inflation is like a bridge connecting the realm of the immensely large, the universe, with the realm of the unimaginably small, quantum physics. It's a theory that operates at the intersection of the grand and the minute, revealing the interconnectedness of all things in the universe. So, buckle up, we're about to embark on a journey that will take us back in time, traversing billions of years to the very beginning of everything. We'll navigate the intricate pathways of cosmic inflation, exploring its origins, principles, and implications. We'll also delve into the evidence that supports this theory, as well as the challenges it faces. As we journey back in time, let's delve into the roots of this theory, the Big Bang. The universe as we know it began with the Big Bang. This theory, a cornerstone of cosmology, paints a picture of the universe exploding from an extremely hot and dense state about 13.8 billion years ago. This explosion set the stage for the universe's expansion, a process that continues even today. Our understanding of the Big Bang theory has been shaped by various observations such as the redshift of distant galaxies and the cosmic microwave background radiation. These observations suggest that the universe was once in a state of extremely high temperature and density and has been expanding and cooling ever since. However, as powerful as the Big Bang theory is, it leaves several questions unanswered. For instance, why does the universe appear so uniform and isotropic on large scales, despite the fact that light from opposite ends of the observable universe hasn't had enough time to meet and exchange information? This conundrum, known as the horizon problem, is one of the key challenges that the Big Bang theory struggles to explain. Another puzzle is the flatness problem, which revolves around the question of why the universe is so close to being geometrically flat. According to the Big Bang theory, for the universe to be as flat as it is today, it would have to have started off in an incredibly, almost impossibly precise initial state. The Big Bang theory also lacks an explanation for the origins of the large-scale structure of the universe. How did galaxies, clusters of galaxies, and vast cosmic voids form from a universe that was initially almost perfectly smooth? In addition to these, the Big Bang theory also struggles with the monopole problem, the mystery of why we don't see any magnetic monopoles in the universe, despite predictions that they should have been created in large quantities in the Big Bang. These questions and challenges paved the way for the formation of the inflationary model, a revolutionary concept that promises to shed light on the mysteries of the early universe. History is full of revolutionary ideas that challenge the status quo. The inflationary model was one such idea. In the early 1980s, cosmologists were grappling with some puzzling questions about the universe's infancy. The Big Bang theory, while powerful, left a few gaps in our understanding of the universe's early moments. Enter the inflationary model, a radical departure from the conventional narrative. The brainchild of physicist Alan Guth, the inflationary model proposed a breathtakingly rapid expansion of the universe in its first moments. This was not a minor tweak to the existing theory, but an audacious leap that sought to explain the unexplainable. Guth wasn't alone in his quest. Andre Linde, Paul Steinhardt, and others contributed significantly to the development of the inflationary model, enhancing and refining Guth's initial concept. Together, they laid the foundation for a new perspective on the universe's early evolution. But why was there a need for such a model? Well, the universe, as we observe it, is remarkably homogeneous, meaning it looks pretty much the same in all directions. The Big Bang Theory had trouble explaining this uniformity. Also, the universe appears flat, another conundrum the Big Bang Theory struggled with. The inflationary model, with its rapid early expansion, provided an elegant solution to these issues. It suggested that the universe expanded so rapidly in its first moments that any initial irregularities were smoothed out, resulting in the homogeneous and flat universe we observe today. This was a radical idea, one that dared to look beyond the established framework and provide a new way of understanding the universe. It was a bold leap into the unknown, a leap that would prove to be a game-changer in the field of cosmology. Armed with the inflationary model, scientists began to unravel the mysteries of the early universe. The inflationary model brought with it new principles that changed our understanding of the universe. At the heart of this model is the concept of rapid expansion. Picture the universe, not as a static, unchanging entity, but as an ever-expanding balloon, growing at a mind-boggling rate in its earliest moments. This concept of inflation, of a universe swelling from a size smaller than a proton to a vast cosmos in a fraction of a second, is a cornerstone of the inflationary model. But why did we need such a model? What was it that the earlier Big Bang Theory couldn't explain? Well, that brings us to two major conundrums that puzzled physicists: the horizon problem and the flatness problem. The horizon problem is a question of uniformity. Look at the cosmic microwave background radiation, a relic of the universe's early moments. It's remarkably uniform across the sky, despite areas being so far apart they couldn't have exchanged information or thermalized to reach the same temperature. How could parts of the universe that have never interacted be so similar? Inflation provides an answer, suggesting these areas were close together before the rapid expansion, allowing them to communicate and become uniform. Now let's tackle the flatness problem. This refers to the apparent flatness of our universe. According to the Big Bang Theory, for the universe to appear as flat as it does now, it must have been incredibly, implausibly flat in its earliest moments. With inflation, this isn't an issue. The rapid expansion could take a universe that wasn't particularly flat and stretch it out, smoothing any curves until it appears flat. These principles not only addressed previous concerns, but also opened a new world of possibilities. They suggested a universe that was dynamic, ever-changing, and full of mysteries yet to be uncovered. The inflationary model doesn't just provide answers, it opens up new questions, new fields of study, and new ways to understand our remarkable universe. A theory is only as good as the evidence that supports it. And when it comes to cosmic inflation, there's a wealth of evidence to delve into. Let's take a closer look, shall we? Our first stop on this journey of discovery is the cosmic microwave background radiation, or CMB for short. This radiation, discovered back in the mid-20th century, is a sort of cosmic afterglow of the Big Bang. It's a snapshot of the universe when it was just a baby, only a few 100,000 years old. When we look at the CMB, we see a remarkably uniform pattern, with only tiny fluctuations in temperature. This homogeneity is exactly what the theory of cosmic inflation predicts. But the CMB isn't just uniform, it's also isotropic. This means it looks the same no matter which direction we look. This isotropy is a bit of a puzzle if we think back to the Big Bang. How could distant regions of the universe, which shouldn't have been able to influence each other due to the speed of light limit, have ended up so similar? Again, cosmic inflation offers an explanation. The inflationary period would have allowed these distant regions to be in contact before they were whisked away from each other by the rapid expansion of space. Moving away from the CMB, let's turn our attention to the large-scale structure of the universe. When we look at the distribution of galaxies and clusters of galaxies, we see a sort of cosmic web, with structures on a vast scale. This pattern of structure formation fits with the idea of inflationary fluctuations. Tiny quantum fluctuations in the early universe magnified to cosmic scales by inflation could have served as the seeds for this structure formation. So from the uniformity and isotropy of the CMB to the large-scale structure of the universe, the evidence points towards cosmic inflation. Of course, science is always about refining and questioning our understanding, but as it stands, the evidence paints a compelling picture of a universe shaped by cosmic inflation. Inflation didn't just stretch the universe, it also set the stage for the formation of cosmic structures. This might sound like a far-fetched idea, but let's break it down. In the early moments of the universe, during the inflationary period, there were quantum fluctuations. Quantum fluctuations are temporary changes in the amount of energy in a point in space, as allowed by the Heisenberg uncertainty principle. Now you might be wondering, what does this have to do with the structure of the universe? Well, these quantum fluctuations got stretched out by the rapid expansion of the universe during inflation. These stretched out fluctuations then became the seeds for the large-scale structures we observe in the universe today. Think of galaxies, galaxy clusters, and even the vast cosmic web. All these owe their existence to those minute quantum fluctuations during inflation. The inflationary model, therefore, offers a compelling explanation for the large-scale structure of the universe. It tells us that the universe we see today, with clusters of galaxies strung out like cosmic jewels across space, emerged from tiny energy fluctuations in the fabric of space-time. This perspective is awe-inspiring, isn't it? The grandeur of the universe, the galaxies, stars, planets, and everything we know, all trace back to the tiniest quantum blips in the early universe. It's like finding out that the magnificent oak tree sprung from a tiny acorn. Inflation, thus, provides a foundation for understanding the universe's structure. It helps us make sense of the universe's large-scale structure, linking the vast cosmos we see today to the tiniest fluctuations in the early universe. It's a testament to the power of scientific theories to connect the smallest scales to the largest, the earliest moments of the universe to its current form. And that, listeners, is the magic of cosmic inflation. Like any scientific theory, the theory of inflation has evolved over time. As our understanding of the universe deepens, new models of inflation emerge, each with its unique perspective and predictions. One of such models is the chaotic inflation model, proposed by André Linde. This model suggests that the universe underwent an endless series of inflationary expansions, creating a multitude of bubble universes, each with different physical properties. It's a fascinating idea, isn't it? A cosmic landscape teeming with universes, each born out of chaotic inflation. Then there's the new inflation model, put forward by Alan Guth and others. This model proposes a period of slow-roll inflation, a brief but intense phase, where the universe expanded exponentially. This model addressed some of the initial concerns with the original inflationary model, giving us a more nuanced understanding of the early universe. But wait, there's more. Let's not forget about eternal inflation. This model suggests that once inflation starts, it never completely stops. Instead, it continues forever in some regions of the universe. It's a mind-bending concept, painting a picture of an ever-expanding cosmic quilt. And these are just a few examples. There are many other variations and refinements, each contributing to our understanding of cosmic inflation. Some models focus on the role of quantum fluctuations, others on the behavior of exotic forms of matter, and some even explore the implications of string theory for inflation. What's remarkable about these different models is that while they may vary in their specifics, they all share a common thread. They all posit that the early universe underwent a period of rapid, exponential expansion, smoothing out its wrinkles and setting the stage for the formation of galaxies, stars, and planets. It's this shared foundation that unites them under the banner of inflationary cosmology. Despite their differences, all these models share the core idea of cosmic inflation. They each offer a different lens through which we can explore the mysteries of the early universe. And in doing so, they bring us one step closer to understanding our cosmic origins. No theory is without its critics, and cosmic inflation is no exception. Even as it resolves some of the most perplexing questions about the early universe, cosmic inflation has its own set of challenges and criticisms. One of the key criticisms is that inflation is considered by some to be unprovable. While we have substantial indirect evidence, such as the uniformity of the cosmic microwave background radiation and the large-scale structure of the universe, there is yet no direct evidence of inflation. This leads some scientists to argue that inflation is more of a philosophical speculation than a scientific theory. Another criticism is that the inflationary model seems to require a fine-tuning of initial conditions. This means that for inflation to occur, certain parameters need to be set within a very specific range. Critics argue this contradicts the naturalness principle, a guiding tenet in physics that discourages theories requiring precise fine-tuning. In addition, the inflationary theory has been challenged by alternative models of the early universe, such as the cyclic model, which proposes a universe that undergoes continuous cycles of expansion and contraction. There's also the string theory landscape model, proposing a multiverse where our universe is just one among a vast number of universes, each with different physical laws. Yet it's important to note that these criticisms and alternatives do not invalidate the inflationary model. Rather, they push the boundaries of our understanding, inviting us to probe deeper into the mysteries of the universe. The ongoing debates within the scientific community serve as a testament to the vibrancy and dynamism of cosmology as a field of study. These debates are far from over, and as more data is gathered and new theories are proposed, our understanding of the early universe will continue to evolve. After all, science is a journey of discovery, constantly challenging our perceptions and expanding our horizons. These debates continue to shape our understanding of the universe. What if our universe is just one among many? This mind-bending question brings us to the fascinating realm of the multiverse hypothesis. This idea suggests that our universe, the vast expanse of space and time that we call home, might actually be just one of countless universes. And the theory of cosmic inflation, which we've been exploring, can provide a pathway to this astounding possibility. Let's delve into the connection between cosmic inflation and the multiverse hypothesis. The concept of cosmic inflation tells us about the rapid expansion of the universe in its earliest moments. During this period of exponential growth, regions of space were flung apart faster than the speed of light. This meant that some regions of the universe were pushed so far apart that they became completely disconnected from each other. These disconnected regions, according to some scientists, could have developed into universes of their own, separate from ours, each with its own laws of physics and properties. This, in essence, is the multiverse hypothesis. But how does inflation lead to multiple universes? The answer lies in the concept of eternal inflation. This is the idea that once inflation starts, it never completely stops. In some regions, inflation might slow down, allowing galaxies and stars to form, as happened in our universe. But in other regions, inflation could continue indefinitely, creating a never-ending production of new universes. This is where the multiverse comes in. Each of these universes, birthed by eternal inflation, could be drastically different. Some might be similar to ours, while others could be wildly different, governed by unfamiliar laws of physics. It's a staggering and somewhat humbling idea, isn't it? The universe that we've been striving to understand, the one with its galaxies, stars, and planets, might just be a tiny bubble in a vast cosmic sea of countless other universes. The concept of a multiverse challenges our understanding of reality, as does the theory of cosmic inflation. And as we continue to probe the mysteries of the cosmos, who knows what other startling revelations await us? Our journey through cosmic inflation has been a journey through the very fabric of the universe. We've been on a voyage from the birth of the cosmos to the formation of everything we see around us today. We've grappled with the mystery of the Big Bang and the questions it left us unanswered. We've seen how cosmic inflation, a theory born of these questions, revolutionized our understanding of the universe's earliest moments. Through the lens of cosmic inflation, we've seen the universe expand at a phenomenal pace, smoothing out into the vast, homogeneous expanse we observe today. We've seen how quantum fluctuations, magnified by inflation, seeded the galaxies and clusters that dot the cosmic landscape. And we've glimpsed into the tantalizing possibility of a multiverse, a world beyond our own cosmic horizon. As we continue to explore the cosmos, theories like cosmic inflation guide us on this fascinating journey.